Okay, looks like they put me on the clock, so let's go ahead and get going. I'm Dan McCleary. This is the somewhat opaquely named Smart SQL processing on databases, Hadoop, and beyond. Thank you all for coming to see the talk. I know I'm standing between you and cocktails, so I will try and make it worth your while and at least give you something to talk about over drinks. So, safe harbor statement, I'm a product manager, so anything I tell you may seem like fantasy, but in fact, there's no fun speaking at Hadoop Summit if you're not talking about something technical and you're not talking about something real. So a lot of what I'm going to be doing is telegraphing and telling you about things that are going to be very real and very material to Oracle this summer. I'm going to talk about three things. We have to take a brief detour in implementation and customer land. And I think that's interesting and relevant because when you work at Oracle, you don't engineer for the Valley. You engineer for the rest of the world. You engineer for the Midwest. You engineer for Johannesburg. You engineer for Sri Lanka. Places that don't necessarily have the raw technical capability that we have right here in this room. I'm going to talk about a broader problem that we've seen over the last couple of years at Oracle with our customers who are embracing Hadoop, and as we embrace Hadoop ourselves, which is how do you make Hadoop a first-class citizen in large information architectures throughout the world. And then finally, I'm going to talk a little bit about smarter SQL processing, which it seems like we've kind of caught the zeitgeist here. Everybody seems to be saying something or another about SQL and Hadoop. So just a snapshot of what Oracle customers look like. I'd mentioned that we engineer not for the Valley, we engineer for the rest of the world. And if you look at these three customers, Thomson Reuters, obviously global company, headquartered in the US, in the Midwest, in fact. CaixaBank is Spain's largest retail bank. BAE Dedica is a large systems integrator that does cybersecurity, a number of other things, largely headquartered in Britain. They're all doing big data with Oracle, and they're all doing very different things. Some are concentrating on data science, some are concentrating on network intrusion, some are revamping their entire business around the notion of data as a first-class asset. One of the things we've noticed is that I point out that they deploy on Oracle systems, and that's good for us, but that's maybe not relevant to you in the audience. What is relevant is they're deploying Hadoop next to databases, tightly conjoined. And whether they do that on our systems or anybody else's systems, there's something fundamentally interesting about that. That, as Merv said in the keynote this morning, this is an adjacent technology. This is a space that is growing, but is a space that is growing adjacent to an existing information architecture. And there's a reason our customers are doing this. When I talk to our customers, they're very plain with us about the fact that we have a very good database, and it's good at some things. But Hadoop is better at other things. And our customers want the best of both worlds. Everybody, in general, wants the best of both worlds. And as developers, we know that one of the first things we're taught is to try and be dry, right? Try not to reinvent wheels. Try not to repeat yourself. And thus, when we take a look at what our customers are doing in the big data space and how we can best enable them, we ourselves are very conscious not to reinvent wheels and to not try and subsume the functionality of a class of technology that's rapidly innovating and providing solutions that we don't inherently provide in our core products. And as such, we've begun to talk internally at Oracle about redefining the notion of what data management means for us. And to some extent, we believe that the era of the DBMS is, if not over, but at least changing. And the time has come to move from the DBMS to the cutely named BDMS, the Big Data Management System. And that encompasses the entire spectrum from relational databases to Hadoop. And for businesses, for the people who end up paying our salaries, this means specific things. Relational databases, data warehouses are sticking around because they run businesses. They integrate systems, they support mission-critical tasks, they keep us from being audited by the SEC. Hadoop and the technologies that have grown up around it represent a fundamental opportunity to reinvent our business architectures, to reinvent our data architectures, and to change the way we do business, to disintermediate, to disrupt, and to leverage new paradigms of computing. And that's exciting. And somewhere in the middle, there's a host of NoSQL databases that allow us to scale out in ways that we couldn't economically do before. So this is important to our customers unless it becomes important as we consider the future of ourselves as a data management company. We are going forward focused on big data management systems, not simply database management systems. And there's a reason for this. And a lot of it is that when we look at the last 5 to 7 years, the Hadoop ecosystem represents remarkable innovation. From HDFS and MapReduce through newcomers like Spark, we see huge advances and an incredible pace of innovation. And we leverage this internally. Oracle Support uses MapReduce to process hardware logs. We have new products being built on Apache Spark. And we're really embracers of the pace of innovation that Hadoop represents. But we've also found, both in our own deployments and in customer deployments, that when you have this pace of innovation, challenges necessarily arise, and arise perhaps more quickly than they did 10 or 15 years ago. And we think, in general, these challenges break into 2 categories: operational challenges and linguistic challenges. The operations challenges are the same sorts of things you see anytime you're trying to stand up a new technology in a data center or potentially build out a private cloud. You have to assemble stuff, you have to integrate hardware and software, I've got to get my versions right, I've got to make sure that I've got all the right patch sets in. How do I do DR in this? Do I need 2 systems? What's the support policy for this? Is it 24/7? Can I actually call somebody? There's a whole lot of that our customers expect, and I think many organizations have come to expect. But there's also a tremendous amount of complexity in language. If you have existing SQL skills, or you have existing, heaven forbid, PL SQL skills, or COBOL skills, or C skills, they don't readily translate to Scala. Some principles do, some don't. But some of the APIs around tools like Pig have been in flux over the last couple of years, and they're getting better and they're getting more stable. And so when we go to roll out big data systems, and when our customers go to roll out big data systems, they're usually looking to solve both challenges as simply as possible. First, they want to make operations as simple and as painless as possible, because nobody likes to get woken up to change a disk. And then beyond that, they're looking for ways to define platforms that allow them to build well today and well in the future. So over the past couple of years, Oracle's been focused specifically on the operations side. We've been looking at how do you put Hadoop into a company in Johannesburg, into a company in Sri Lanka, and have it stand up, and have it be operational. And we took some experience from what we'd done with databases. So if anybody knows what an Exadata is, this is our premium engineered system for Oracle database. What this thing does is it kills ops problems. If you've got 100 Oracle databases that are running slow on HP Superdomes, you've got operational challenges, you buy one of these, you put it in, and all of a sudden your ops problems are basically gone. And there are lots of reasons for that, right? So we tune the thing, we optimize it, we make upgrade easy, we manage the whole darn thing. But we charge a hell of a lot of money for it. It's $1 million box. And that won't cut it in the Hadoop world. So when we set out to solve operational challenges in the Hadoop world, we had to ask ourselves questions about what is optimized for operations and engineered for scale for Hadoop really mean. And what we came up with was a system which released rapidly, kept up with the community, had members of the development team trying to commit back, and then wrapped up the operational challenges without messing with core Hadoop, providing easy upgrades, rapid provisioning and multi-tenancy, on-disk encryption, setup of all of the little niggly things you don't necessarily want to deal with, like LDAP and Kerberos, and just did all of that out of the box, but provided an open platform where people could actually begin to build using these new technologies. And to do that, not at the $1 million price tag, but at something that looked a lot like what you could buy off the shelf, your own kit. So we felt like this pretty well solved the operational problem. But a couple of years on, we don't feel like that's really what's holding big data up. And Merv talked about this a little bit this morning, many other people talked about it. There are a number of people who are still waiting for Hadoop. And so what are the barriers for that? Well, when I think about it, I think there are known barriers to adopting big data that we never want to talk about. The first one, anybody in this room is probably already being contacted by recruiters, right, is that Hadoop requires new expertise. Is anybody in here a Hadoop expert, a MapReduce expert, a Hive expert, a Spark expert? Raise your hand if you are. Please, somebody must be, right? I mean, that's why we're here. All right, we got a couple, and I know Ali is. But there's nothing wrong with that. I think a lot of talks around, oh no, Hadoop is too hard to use, there's a skills barrier. Like, no, it's good. We want new experts. But is anybody here a data management expert, a SQL expert, an informatic expert? Anybody want to raise your hand? Good. Good. More experts is better. What we need to do in order to make Hadoop a first-class citizen in enterprise environments across the world is to let experts be experts. If you have expertise in SQL, in security, in data management, in backup, that's wonderful. Experts solve harder problems faster and more efficiently. However, if you're a Hadoop expert, that's even better because there's a new class of problems opening up for which your expertise can now be brought to bear. However, we need to be able to make sure that experts can work together. Your Spark expert needs to be able to talk to your security expert, needs to be able to talk to your network expert. At the point at which that happens, we can start to ensure that Hadoop doesn't become a silo. In some of our customer deployments, we find that customers are successful with big data projects. They've found a use case. It's great. They're driving value. But there's no way to bring that home into the core operation of the business. And we need to find some way to make sure that that interoperability is there, that that bridge is there. And it's been said many times, and apparently there have been a bunch of acquisitions around it in the last week or so. But security is an issue. If you work in a regulated environment, security really matters. And between Knox and Sentry and a number of other different approaches, there's no real clear route to governance or enforcement. There are lots of efforts that are going on, and it's going to be a very different story in a year. But it's important, and it is causing some industries to sort of lag. So these are the barriers we see when it comes to adopting Hadoop worldwide in all manner of businesses. So how do we make Hadoop a first-class citizen? There are lots of different ways to do this, but Oracle is a database company, which means we have a very particular kind of hammer. Surprising? I didn't think so. But why? Why is SQL the way that we think is simplest to make Hadoop a first-class citizen and an equal member of IT infrastructures worldwide? Well, some of it is because we like SQL, and we tend to think we know a lot about it. But when we go back to core principles, we think that some of it actually might have to do with this. If you wrote this query in 1974, when SQL made its very, very first sort of instantiation, it worked. And you can run it today. And what it does is it still works. And it works faster, and it works in more places. It's a pretty good bridge. So SQL and Hadoop is obvious, right? Everybody is doing this, and there are lots of great projects which do it. And there's a reason SQL and Hadoop is obvious. And it's not just that it's a fourth-generation language. It's not just that it's descriptive. It's that SQL provides a unique language for data in which you describe the answers you want, the shape of the answer that you want. And you don't have to worry about the data access path. You don't necessarily have to worry about the optimization. All you have to say is, I have some sets of data. I would like an answer like this from it. Please go get it. And after that, other systems take care of it for you. It's very, very good for enhancing productivity. So we really welcome and support many of the SQL and Hadoop efforts. We think it's fantastic. However, data lives in many places. We know because we own some of those places. And when we're realistic about where data lives in our customer implementations, we often find that Hadoop is a source for application logs, for images, for a number of kinds of data that are really compelling and really interesting. Similarly, key value stores are fantastic for all kinds of things that Web 2.0 applications or mobile applications are using. But some things are never leaving the database. P&L, general ledger, these things that businesses cannot let out of their sites lest they get shut down will live in relational databases. And so our challenge, and I'm a person who lives very much at the intersection of Hadoop and the database, is that I want to do this. I want to write that one SQL statement that worked in 1974 and have it work faster and in more places, but in more places at once. So that's the challenge for us at Oracle. And I think more broadly, I think it's the challenge for the Hadoop community as a group of developers and enthusiasts who are rapidly innovating. What we want is a system that gives us the full power of a language like SQL, this ability to simply ask questions without knowing the route to the answer, and allows us to integrate any application we might have today and integrate any application we may have tomorrow without really changing our access patterns, and gives us a single view of all of our data. If we're going to ask bigger questions, we need to be able to see all of our data, whether it's in the relational database or in Hadoop. And at the same time, we don't want to break anything, right? We don't want to have to change Hadoop to make this work. And we want to make sure it's still performant, and we want to make sure anything else you do on Hadoop is performant. If you want to run MLlib on your data in Hadoop and you want to run SQL on it, that should all work fine. So what we've been working on at Oracle over the past while is this notion of smart SQL processing on Hadoop and a lot more than Hadoop. And hopefully, 100% of you are wondering how we actually do this, because we are actually doing this, and this is a real thing. So our requirements going into this were we had to have full SQL, full Oracle SQL, ANSI 2011, no changes to BI applications, no changes to any application using JDBC or ODBC, with a single view of all the data and the fastest performance we could get without changing Hadoop. And if we could, as a bonus, if I want to get my bonus this year, I suppose, we wanted to unify metadata so that we could see data in the relational system, data in Hadoop, and maybe just run queries on Mongo or Cassandra or Redis or anything else that maybe supports certain interfaces. So here's what we did. Right? The first thing we did is we taught the database about Hadoop. Right? We gave the database the ability to be a Hadoop client in a way that wasn't stovepiped. The second thing we did was we expanded what we consider our database metadata, our catalog, to understand objects that live in Hadoop. And then the last thing we're doing is we're adding services to the Hadoop ecosystem to execute and optimize data requests on our part. So now we can actually start to get technical. So how did we teach Oracle about Hadoop? And it was very much teaching Oracle and Oracle developers about Hadoop. How did we make this work? So we went back and sat down and with a bunch of the parallel execution engineers and said, well, let's talk about how MapReduce processes data. It starts with a scan. Pretty much everything starts with a scan. But once I scanned things out of Hadoop, the natural question that came from a lot of database engineers is, well, it's a key value. I don't understand how we're going to get this into database formats. We deal with rows. We deal with tuples. Well, one of the fortunate things about the way Hadoop as a set of APIs has grown up is that there are known classes and interfaces which help us get the information we need. And two of the most important, and I feel like they're not nearly talked about enough, are the input format and the record reader. And if you don't know specifically what these do, I'll tell you. The input format really defines parallelism. We all know that data gets replicated 3 or more times in HDFS. But when you go to read that in a MapReduce job, you're using this interface, this input format interface, to get input splits, which tell you where your blocks live and how you should break up your processing. And then the record reader class tells you how to get those key value pairs out. And what this is doing from the perspective of a database engineer is it's making rows. OK, well, we know about rows. If we can make rows, then maybe we can make this go. So then what does Hive do? What does Hive add? It adds a couple of things that are very important to at least the database engineer's understanding of what we can do in this environment, what we need to do in this environment. Well, it does a couple of things. Hive gives us a place to put DDL down. Right? We can write DDL, and all of a sudden we have a description of what the shape of that data as tuples is. Right? So we've got rows and columns. And when you write that information into the Hive metastore, you're laying down information about the input format and the record reader and a SERDI. And that SERDI is going to tell us how to make columns out of the rows, and that's important. And there are some other things that go along with it. You might have table properties, you might have a storage handler, you might have partitions, you might have any number of other things. But for the purposes of this discussion, these 3 classes are key, because now I know how to go from a scan, and a scan is pretty much the same anywhere you do it, into rows and columns. And rows and columns are things that databases understand. OK. Well, let's now talk about how I would expose that kind of a mechanism to the Oracle database in a way that isn't stovepiped. Well, the first thing I'm going to do is I'm going to publish that metadata, that information I need about parallelism, input format, right? How to read rows, record reader, and how to make columns, the SERDI, into our own data dictionary. Why our own data dictionary and not something else? Well, DRY, right? We already have a pretty good catalog that we know how to work with, so publish it into our catalog. And now we can use our external table interface to say, oh, I have a table, it's got some information about it. It's different information than I've ever dealt with before, but I know how to talk to it. And at this point, now I can start to write tables, right? I can start to define tables. And so if you look at this table, this is actually a SQL statement you'll be able to run this summer, where all of a sudden I have an Oracle table that has Oracle types, but is organized to use Hive as part of its catalog. And what I get out of that is baked into my table definition without having to write anything. I get the SERDI for columns, the record reader for rows, the input format so I get native style parallelism from Hadoop, and bonus for those of you who know about storage handlers, I can reach out to almost anything else. Now I need to go execute a query. OK, I've got some metadata. This is good. So I have a little SQL statement here. I want to select a few columns. And maybe I want to join it with some data that's in my Oracle database. Well, what I'm going to do when that query compiles, and all queries compile in all databases, whether they're interactive or not, is I go out to the name node and the metastore, and I determine what's my parallelism, where does the data live, and how am I going to read this? What classes do I need to go read this? Once I've done that, all I do is I send specific requests to different data nodes to give me their blocks. And then I can go and process them using the same classes that they would be read by in anything else using an input format. That's good. This is a very native sort of way. This is almost like MapReduce, but with native SQL operators. And that's OK. That's really the Oracle database starting to learn how to speak natively to Hadoop. But oh, I'm sorry. Apparently there's a bottleneck. Does anybody know what the bottleneck here is? It's a remote read. And so even though I have a massive parallel execution server in an Oracle database, there's a network in between. And anytime you got to move data over a network, it gets slow. So how do we make this processing smarter? At this point, I've defined an interface by which my Oracle database can very natively talk to Hadoop. That's pretty good. I can pick up lots of other definitions, but I got to make this smarter. So we asked ourselves internally, what can we learn from the Exadata team, right? So not just raise the cost of your hardware, because that's one thing we could have learned from them, but we actually pulled the Exadata engineers in and sat down with them. I'm like, OK, what makes Exadata go fast? And their first answer was, well, we cheat. I'm like, well, what do you mean you cheat? Well, we do all the operations on the other side before we get to the network. I'm like, all right. So what it boils down to is that if you can minimize data movement, you can maximize performance. And in fact, if anybody caught the BlinkDB talk earlier today, much of the notion of sampling data is that you're moving and processing even less data, which means you go faster, right? Cut down the data by an order of magnitude, go an order of magnitude faster. So Exadata does this using three things. I call them smart scan, storage indexing, and caching. And caching, I think we all know, right? If I store data in memory, it's easier to get to. If I store data already in the format I needed, it's easier to get to. Smart scan and storage indexing are perhaps Oracle-specific terms. And what they boil down to is this. Smart scan filters data as it's being scanned on the disk. Storage indexing ensures that I only scan data I should scan. So what does that mean? Well, it means a couple of things. We're going to have to put a service on Hadoop. We're going to have some new member of the ecosystem that happens to live there. So we're going to put a process on every data node that simply listens to our requests from our database and performs those scans for us. And it's going to go ahead and make tables for us. That's good. So now all of a sudden, I'm doing all of my reads over there. I'm doing all of my type conversions over there. And I'm only sending across Oracle rows. That's good. But now let's try this smart scan concept. What I'm going to do now is I'm going to scan that data off of disk, apply the Hadoop classes necessary to get it into rows and columns. And now I'm going to start to filter stuff out. I'm going to filter out rows that don't have any relevance to the query that you wrote. And then I'm going to project out the columns that you asked for and not any of the others. Right? So within our couple of tables, which may represent several hundred terabytes of data, I'm actually only going to pick out the couple of values that you care about. And only those values are going to go on the wire. Well, at this point, I've probably cut down the amount of data. If we're talking about hundreds of terabytes of data in HDFS, and you're only asking a query that maybe covers 2 columns, I'm moving far less data across the wire. And that's good. I'm still, though, reading a lot of data off of disk, which means I'm still relatively I/O bound. It's all right, though. I can apply this join, and all of a sudden, I have data in my relational system. I've got that general ledger that I can't live without. And I've got that new data that I want to store in Hadoop. And I can join these things together. I can ensure that I'm moving a minimum amount of data. My Hadoop cluster still operates like a Hadoop cluster, just has one more service on it. And my database still feels like a database. All of a sudden, everybody's skills are relevant. So let's go a little bit farther. How do I make sure that I spend less time reading the disks? So this is this notion of storage indexing. So the first time you scan a table in Hive, a set of blocks in HDFS, as our service processes that data coming off of the disk, we're going to keep track of what we saw. We're going to keep track of the minimum value we saw for each column, the maximum value we saw for each column. And we're going to call that thing a storage index. Effectively, this is a really small structure that tells me, for this inputs format, for this split, I have for column A, this is the min, this is the max. For column B, this is the min, this is the max. The next time you run a query on that set of splits, I'm going to look at that index first and say, oh, well, the where clause on this query says that they're looking for salary greater than 80,000. Nothing in this block has that. Don't get it off the disk. Don't do the scan. Fewer scans I do, less time I take. So what happens? All of a sudden, I have a service resident on Hadoop that reads data for you only when you need it read and transmits back data only when it's relevant to your queries. Otherwise, we skip it and we just go faster. So that's technically interesting, and I could talk to you guys all day about it. But what does it mean for you, not for me? What it means for me is a lot more work. But what does it mean for you, and what does it mean for making Hadoop a first-class citizen? So the question I would like people to ask themselves as they leave this talk is, what would you do if you could query all of your data in a single statement? Right? What if you could store JSON data in Hadoop coming off your app servers, and the business-critical data that comes from your transactional systems in, say, Oracle database, and you could just write SQL queries across all of it? Well, in this system, in our big data management system, what you'll find is that when you go to do this join between the revenue numbers you keep in your database and the JSON you keep in HDFS, what we'll push down to that smart service is the processing of the JSON, the columns, the column projection work that you need, and a Bloom filter to make the join faster, too, because you probably have far more app logs than you do revenue data. So we'll look at the revenue data first, scan it, compute a Bloom filter, push that down, and make sure that we only send the columns of the JSON records that are actually useful. And all you have to do is just write a little statement like that. All you have to do is describe the answer you want, not how to get it, not how to build the filter, not how to parse the JSON. Store data in the format it arrived, in the place it makes the most sense, and process it all with one language. Now, security's been a big theme throughout the day, and we tend to know a lot about security in the database world because we work in a lot of regulated industries. So let's take the same use case. And what if we could govern all data from an application standpoint? What if we could actually put real policies or extend existing policies to all data? So take the same example. I have JSON data in HDFS. I have business data in Oracle. I want to write SQL against it, but I'm not allowed to see certain things. I'm not allowed to see bank account values or social security numbers, credit card numbers. Well, the way we would do this in a database is we would add, say, a redaction policy. We would just write a little thing like this that says people who can't see credit card numbers see a masked version. They see a random version. And what we'll do is we'll apply masking and redaction to all data streaming off of those servers. We will allow things like virtual private database, which gives you row and cell level security. Fine-grained access control, actual fine-grained access control. And we're actually going to use, effectively, the same database management system techniques we've used for security all along. And this is a real benefit for anybody who's got security skills, because if you used to assume that there was a DBMS at the bottom that provided security, there is still a DBMS in the picture providing security, and you can just extend roles and policies based on what your existing enterprise already has. However, we're keeping Hadoop free and open. So if your group of data scientists need to run PySpark on that same data, and they have privileges that allow them to see everything, that's fine. We won't mask it, we won't redact it, we won't get in the way. But if you have an application or a user coming in through the database that needs to be restricted, we just apply it as part of our Smart SQL processing. So that's what we have coming this summer, right? In Oracle's vision of the future, in our vision of a big data management system, what we want to do is provide one fast SQL query on all your data. And so what you'll see this summer is Oracle SQL and Hadoop and beyond on any database that supports a storage handler. With a smart scan service, the same as you see in Exadata, with native SQL operators. There's no MapReduce here. There's no federating with external processing engines. These are our own native operators, so we get maximum expressiveness. With the security and certainty that those of you who've come to expect it from an enterprise-class DBMS expect to see. So happy 40th birthday, SQL. 40 is the new 30, is the new 20, is still relevant. So if any of you are interested in finding out more about this, you can follow me on Twitter. I don't tweet that much, but I try to make it funny. Or you can go to, oracle.com, Big Data Breakthrough. And about a month from now, we'll be doing a webcast, myself and Andy Mendelson, Executive Vice President of Database Development, actually demoing the technology, actually going through it. And there'll be a lot more about it later this summer. And so that's it for me. If anybody has questions, I'd be happy to take them. For those of you who are running off to the bar, I'll see you soon. Initially, that's the plan. But there's nothing about this technology that says it has to be on our engineered systems. So that's a very good question. Will we maintain SERDES? Because what if you wrote a SERDE? What if you have an evolving definition of things? And so the idea is, if you have your own SERDES, bring them. We'll run them. If you have your own input format, bring it. We'll run it. It's open. However, for those things which are core and are already widely used within the Hadoop ecosystem, they'll be supported and in part maintained by us, and in part maintained by Cloudera, and in part maintained by Hortonworks, and in part maintained by the rest of the community. Effectively, if a SERDE runs in Hive, it'll run with this. If it's part of a core distribution, it'll be supported. Well, if I write a SERDE that doesn't work very well, am I going to call up my vendor and say, hey, my code sucks? No. I mean, we will, if it works in Hive, it'll work. It should work in this environment. However, you can't go grab something off GitHub and then call us up and say, hey, this thing on GitHub doesn't work. Unless it's github.com/Oracle, then it's on us. Mm-hmm. And they pretty much get every block index similar to each other. You do not have filtering effects. So to repeat the question, so to make sure I understand it correctly, so are we transforming data on the Hadoop nodes? So the storage index will maintain on local storage because this is local effectively to every processor, every process. But when we scan the data in our scan server, what we're doing is we're scanning it out of HDFS, converting it into Oracle blocks, which is a format we understand very well, and then indexing that. And so, yes, data underneath may change, and that storage index may get stale. And that's a thing that actually rankles a lot of RDBMS developers who expect everything to be exactly right all the time. So what you'll see with this notion of storage indexing is it's selectable. So you can say, I want storage indexing on this because I can deal with slightly stale data, and I understand that that index is built off of transformed data that was built on the fly and may be stale. Or you can say, I need absolute correct, up-to-the-minute results. Don't run a storage index on it.
Transferring data from Exadata node to Hadoop node, like it's a node level, or
how are we transferring data? So effectively, if you look at what Exadata does, when we go to read data out of our storage servers, we send instructions down, right? We send work down, and we get data back, right? So we send some context information, we get it back. And we do effectively the same thing in this case. We treat at query compile, we go out to the name node in the metastore, and we get just the information we need to build context. Then we ship that context to our parallel execution servers, which then ship them to data nodes. So they'll have a set of corresponding data nodes for a given query. And those data nodes will return data directly to their parallel execution servers. So you get massive parallelism from our PX side to the to the data nodes. Good enough?
So you have a two cluster, I would say. So one is your Exadata and one is the Hadoop.
Mm-hmm.
I have some tables in. Let me ask you one question before. So when you move the data out, load the data in Hadoop,
Mm-hmm.
does it always have to go through Oracle to
No.
load that data?
No, you can so you can treat this Hadoop cluster any way you want to. This is part of our commitment to keeping it an open platform.
When do you collect that, you build those storage
When
indexes?
the first time you scan it, on access.
Okay, so the first time I run those queries, it would be slower, right?
Yeah, you may in fact want to just go ahead and run a query on just a select star on this to build your index on it.
And second question is, if I have, 5 tables in Oracle,
Mhm.
7 in, Hadoop, and if I join those guys together,
Mhm.
how does the federation works? I mean,
So it depends on what plan the optimizer comes up with. We have a pretty sophisticated optimizer that's going to look at the entirety of the plan and understand that these 7 are external and these 5 are internal, and what filters can I potentially build.
so they are pre-joined at Hadoop level first, and they are brought the
It depends. It'll actually really depend on what the optimizer comes up with. So are we pushing join work down? Not yet, not yet. But you've identified one of the things that's actually, we look at this architecture and say immediately like, oh, we should push part of the join in. So Bloom filter will give us a bit of the join, but not all of it.
So right now it's not doing that.
So it'll do Bloom filters, but we won't push down part of like semi-join information. That's longer term.
would this architecture allow me to run a query that joins Hadoop and Exadata and store it back as a Hadoop table?
That's a good question. This architecture won't, but some of the things we have coming in the fall will allow you to write data back out of Oracle into Hadoop.
I guess this is a follow-on. Partitioning in Oracle.
Mm-hmm.
Where you want to go and store all your cold data in Hadoop, have your hot data in Oracle.
I like how you're thinking. This is a use case that we're into as well.
So where are you in that use case?
So where we are today is effectively have a partition table of your hot data in Oracle and have the external table of data in Hadoop and union all of them. What we'd like to do. So we would union it to a view. And then what we would like to do is introduce better partitioning for external tables as well. So you could actually have exact partition replicas as you moved things into Hadoop. All right, I got 40 seconds left. Anybody got any last questions? All right, you got 37 seconds.
Last question I have is, how do you ensure with Oracle people expect certain performance after SLAs? In this context now, how do you plan to resource and treating?
That's a good question. So a lot of what we're trying to do in terms of ensuring SLAs, and it's harder when you start talking about a cluster that now has many other services running on it, is we already have an agent that lives on nodes of our big data appliance, which feeds information into Enterprise Manager. We're going to be adding more functionality so that it can feed into SQL Monitor, so it can feed into the Database Monitor plugin for that, so that all of our existing management and monitoring systems that you use to at least derive your SLAs will have some exposed information. Now, granted, I can't predict perfectly what's going on in a cluster that I don't totally control, but we're going to do some resource management with C groups and with Yarn to make sure that these processes actually get dedicated CPU and dedicated memory. All right, 25 seconds left. I'm calling it quits. Everybody enjoy a drink.